This is going to be section 11.5. We'll be discussing a simple pendulum. So a simple pendulum is an idealized model consisting of a point mass suspended from a string of length L. For small amplitudes, the motion is nearly simply harmonic, and the angular frequency is nearly independent of the amplitude and the object's mass. In other words, the angular frequency is going to be equal to the square root of the gravitational acceleration divided by the length of the length of the pendulum. For larger displacements, the frequency depends on the amplitude. So depending on how far out you bring this sucker, is going to make this depend upon the amplitude. So let's take a look at this more closely. All right, so a simple pendulum is an idealized model consisting of a point mass suspended by a weightless, unstretchable string in a uniform gravitational field. When the mass is pulled to one side of its straight down equilibrium position and released, it oscillates about the equilibrium position. Familiar objects such as a wrecking ball on a crane's cable, the plumb bob on a surveyor's transit, and a child on a swing can be modeled as simple pendulums. We can now analyze the motion of such systems, asking in particular whether it is simple harmonic. So the path of the object, modeled as a point mass, is an arc of a circle with radius L equal to the length of the string. So I got this, whatever the point mass is here, we've got L, and we're going to be bringing it out. Obviously, it's got tension in the string. The string is considered to be massless and unstretchable. And we've got the weight of the mass being pulled straight down. Obviously, if we break it into components, we would have a sine component going this way and a cosine component going this way. So we use as our coordinate the distance x measured along the arc. So you can see this distance there along the arc. That's going to be considered to be x. If the motion is simple harmonic, the restoring force must be directly proportional to x or to theta. Question is whether or not it is. X being related to theta, of course, x divided by L is going to give you the angle that is produced. So in figure 11.25, we represent the forces on the mass in terms of tangential and radial components. The restoring force at each point is the component of the force tangent to the circular path at that point. In other words, the force here is minus mg sine of theta. So the restoring force is therefore proportional not to theta, but to sine of theta. So the motion is not simply harmonic. But if the angle is small, then the sine of theta is very nearly equal to theta if you look at it in radians. So in other words, for example, if the angle that you pull it back is about 6 degrees or 0.1 radians, the sine is 0.0998, a difference of only about 0.2%. So with that approximation, we change this into just theta. We know that theta is x over L. And then as we rearrange this, we bring the x over here and we just have mg over L. All of that can be considered to be a constant. So therefore, the frequency and the period of this situation, the angular frequencies, the square root of k over m, k, which we now know is mg divided by L, the m's cancel, and that's the square root of g over L. The frequency is going to be the angular frequency divided by 2 pi, so 1 over 2 pi times the square root of g over L. The period is therefore 2 pi times the square root of L over g. If you've ever heard of a Focal pendulum, it's a very, very long pendulum. The plane of rotation of the Focal pendulum does not change but it's the earth around it that changes. If you've ever seen one of these in a museum, this goes and it knocks over each one of these little setups here in turn. It takes usually about 24 hours for the earth to rotate for the pendulum to knock them all down. It's kind of an interesting little exercise. So the motion of a pendulum is only approximately simply harmonic. For very small displacements, the approximation is quite precise. So in other words, when the angular amplitude is 15 degrees, the actual period differs from our prediction of our approximate analysis by less than 0.5%. So the usefulness of the pendulum and clocks depends on the fact that for small amplitudes, the motion is very nearly independent of the amplitude. You've got a few problems there to work through.